Come on the lecture number 13 of module 2. In the last module we saw that load flow problems, load flow solution algorithm cannot give the solution at the notch point. So in this lecture we will see the continuation power flow method, which can give you the solution at near to the notch curve as well. What is the notch curve? If you remember here, if this is if you draw the PV curve, this is your real power P and this is your voltage V, then this is your PV curve, and the point here, that is also known as a saddle node bifurcation point. Here the load flow solution will not get converged because the determinant of the load flow Jacobian becomes singular here. So we cannot get the inverse of that. Even though moreover that, this is, if you are approaching this point is called saddle node bifurcation point. Before this, here, even though a load flow solution sometimes may not converge due to the ill conditioning of Jacobian, because if Jacobian becomes ill conditioned, the inverse will be not proper, and finally we cannot get the change in the voltage and the angles using the Newton-Raphson method. So this continuation power flow method is the method by which we can calculate even though this whole portion of the solution till the notch point and even all the lower point as well. Now in this continuation power flow methods, which utilizes the conventional power flow methods again, but we go for the several steps, and normally we utilize the two steps. One is called the corrector step and another is predictor step. Means with the predictor step, first we increase the load and then we draw at the tangent point, we linearly calculate this predictors. Let us suppose we start from here at this point, then we can have a transient here vector this up to certain load change. Here the load is changing in the tangent direction, and then this step is called your predictor step. Predictor step, and since we have moved here, then its point is not the actual solution. So our actual solution point is this, so we go for the corrector step, and similarly again the tangent point here, then here, and finally we can reach to the notch point. So this is the sequence of predictor and corrector steps are applied or used in the continuation power flow method. Here what we do, we keep on increasing the load. Load means load at the load buses. So it is a, if there is a one factor that is called lambda, that is a load factor here normally used. If you are increasing from 0, means if 0 means your increase is almost, there is no, it is starting at from the base case. For example, let us suppose we can write the load injection at any bus, that is I can say here Pi, that we can write the power generation at that bus minus P demand at this bus. This P demand I can say not, means it is a base case or the load flow or even initial loading of the bus ith. Now if you want to increase the load at this bus, I can say I can use here 1 plus a term lambda. Lambda can vary from 0 to certain lambda critical value. So if your lambda is increasing, means lambda is 0, means it is a base case solution, base case injection, and then that is the point I can say here at some point here, starting some point. Now once your lambda is increasing, then your demand at that bus is the total demand is increasing by that factor 1 plus here, that is lambda. So here your P injection will be changed, and then we have to solve what will be the voltages and the angles at the various buses in the system. In this continuation power flow program, we can calculate the voltage and angle as well, and the method here we apply the predictor method first and then corrector methods. I will explain these methods later on. Now what this equation, we know that it's a P injection at any bus, that we can write in terms of voltages and the angle functions. Here I can say it is a function of your delta, that is a voltage angle, and here is the V, the voltage magnitude vectors. If you remember in the power flow equations, normally this vector at the ith, I can write here the summation of here Vi, Vj here j is equal to 1 to nb, or you can say n, total number of buses. Here I can write gij cos delta ij plus b sin delta ij. So, this is, we can say, this is a function of voltages vectors and as well as the angle vectors. Here delta ij is equal to nothing but your delta I minus delta j. So, this whole function we can write is a function of angle and voltage. So, in the total, if you include this one as well, so I can say this whole representation can be written in this form, that is of vectors. Here this f is vectors and it is for all the buses except your slack bus, and if it is a real and reactive, since it is a reactive power, a real power, so it will be your n minus 1 equation, and since load flow equation is also for your reactive power, so it will be your n minus nq, and nq is number of generators, reactive power, including reactive power sources. So, the total number of equations here, the power flow, as you know, it is your 2n minus nq minus 1. Now, you can see here we had number of variables now. Earlier the number of variables were equal to the number of equations, and we were able to calculate the values, that is unknown values, and because we had the number of equation equal to the number of unknowns. In this case, we have another unknown, that is a lambda, that we don't know what will be the lambda at this point S. So, right now the total number of variable is 2n minus nq, because another unknown value is used. So, in this case we have the number of equations are lesser than number of unknowns. So, we have to use some mechanism, we have to fix one value, and then we can go for the predictor and the corrector methods. To solve this problem, that is AF, it is nothing but your load flow equation here, including a load parameters, load factor that is changing. So, to solve the problem, continuation algorithm starts from a known solution. Known solution means you have to start from the base case where lambda is 0, and uses a predictor and corrector scheme, means one predictor and one corrector to find out the subsequent solutions at the different load levels. It uses the concept of local parameterization with the lambda included in the load flow. Already we have included here lambda, you can say, you can see here, and here the number of variables are now increased by 1, and total number of variables that to be known here 2n minus nq. Now, here let us see how we can derive. So, the equation which I wrote here, that is the equation here, if you can differentiate, we can write in the differential form with the reference to your delta, voltage and the lambda, we can get this differential equation or this vector, means here one Jacobian here, this is a vector, and that we have the differentiation of the change in the delta, and here this is a factor, that is a differentiation of the voltage, means we are differentiating this function f with respect to voltage, then it is change in the voltage, and here with the change in the delta here we are using. So, in this case you can say the change in the lambda here is one factor here, one factor here and one factor here, and these factors are calculated from the base case value. In this another form we can write here, and that will be 0. Here you can see this is multiplied by here, this is multiplied by here, and this is multiplied by here. So, this is your, we can say it is written in the differential form. Now, what is a predictor step? First, the number of the equation B has the total 2n minus nq variables. However, we have only the equations, again I am repeating, it is 2n minus nq minus 1 equations. In order to achieve the value of the tangent, that is a vector here, the value of one of these, say kth tangent vector, should be specified. What happens here, again if you will see the PV curve. In the predictor step, always what we do, let us suppose this is your actual PV curve, just we want to calculate. If you start from here, then in the predictor step we draw a tangent to this point here, and we need increase the loading, and then we go for the correction step. So, this step is your called the predictor step, and since we have predicted this, basically we go for this calculating this value with the increase in the load, and then keeping the load constant we calculate the actual solution using any conventional load flow algorithms, and normally we use Newton-Raphson method. So, in this, as I said, number of equations are less than number of unknowns, that is 1. So, we have to specify one tangent vector, and here that is your, here the change in the delta v and lambda are nothing but the tangent to this surface. So, let's this t is the here vector, that is here we are vectors, this value, here this value and this value. This lambda is 1 because we are assuming that we are increasing with the constant load factor in this case. So, the lambda delta just we require, it is nothing but your n minus 1, and the v we require n minus nq. So, the total you can see here, it is a 2n minus nq unknowns are there. So, what we do, we choose one kth out of this whole one, we fix either plus 1 or minus 1. We will see which one will be plus 1 or minus 1. So, the equation 2 can be written again. If you will see the equation 2 here, this equation 2 here we can write another one, and that we can add one more equation here to increase the number of equations, so that we can solve it easily. So, Tk here, that's one value we are putting the plus minus 1. So, here we have put it here, and then this is the t is the vector of change in your delta, change in voltage and change in lambda, and this is equation, where this Ek will be nothing but the 0 0 1 and 0 0, this will have only one value, this is the vector here, all the zeros, and one value which will be multiplied by the t, that is 1 is specified here. Means the 1 here out of these n 2n minus nq, 1 will be having 1, and that value will, which one will be fixed 1, it will be carrying only one other will be it is 0. So, all the elements will be 0 except value 1, and that is corresponding to any kth value out of this. Letting Tk is equal to plus minus 1 impose a non-zero norms on the tangent vector and guarantee that the augmented Jacobian will be non-singular at the critical point. Plus 1 value of Tk is taken if the kth variable is increasing when the path is being traced. If you that value, this tangent, all these are the tangent value, if these values are increasing here, taken positive 1 if it is increasing while the tracing, means while going here, if it is increasing, then it will be taken 1, and it will be taken negative when it is decreasing, normally this side it will be taken negative value. So, once the tangent vector has been found, means now we can solve this one easily, we can solve this equation, and now what we can get? We can get the vector t, means we can get here change in delta, change in voltage and change in your lambda we can get here from this one. And then once you have obtained this, then we can add with your starting point, means base case, and then you can add with the sum. Here we have used sigma or scalar value, and that is known as the step size. It should be such that the predicted solution star is within the radius of character, a constant value is normally used. So, we can get the optimal value, and then this is your predictor step. Means from here, from any point in this curve, you have started from A, you have just made a tangent here, and then you have reached at this point, that is your star point which we have written. So, starting with here this lambda here and your v, just we have obtained this. So, we have reached at this point. Now, this point is not the actual solution because it is not on the surface of this curve, means that is approximate solution. So, what we have to do? We have to again go further that correction, that is the error which we have encountered, which has been taken. So, that step is called the corrector step, and that corrector step, just let us see how it is used. This is a correction. In this corrector step, a local parameterization technique can be used to correct the solution. The Newton-Raphson method is used to find the corrected solution by pre-specifying the value of one of the parameter. Means one parameter we have to fix and then we have to calculate the remaining one, and that value which we are fixing here, that is a xk. Xk means any value out of these, all this. This is your nothing but it is x vector. In that you are fixing one and then you are going. Normally this is your nothing but your load. That load you have increased, that is fixed, and the remaining we calculate this. So using the original load flow equation here, that is your fx bar, that is a x vector here, and then we are having fixing one kth variable because we are having more number of unknowns than equations. So we are adding one equation here and then we can solve it, and this is called your corrector step. The corrected state, that is a x bar, here is a this can be obtained by solving them using the conventional Newton-Raphson methods. Xk is known as the continuation parameter. The kth x is known as the continuation parameter, which has non-zero differential change, that is a dxk should be tk, and that is should plus minus 1. In the corrector its value is pre-specified so that other state variables can be obtained. Now you can see in this method what we are doing. If you can see, if you are going for the corrector and the predictor step, let us see here again. This is your, that's we want this PV curve here. Here is starting from this point, and then you have taken a tangent here, and then you are correcting. Here again you have taken a tangent, you are correcting, and here again you have taken a tangent, and then you are correcting. Now you can see the point here at the D, and this is the point E. At the point D, for the corrector step, this will not converge because this is a outside the, it is not solvable point at all. So you cannot solve this one. So what you have to do, instead of the, you can estimate the load. Here what we did, we estimate the load, we have just moved here tangent vector, we estimated the load here, then at that load we got the solution, and then point E, here you can say point whatever you can say B. From B we took here the one tangent, we move at the D, but this D point here is out of the solution, means unsolvable. Again the non-convergent and unsolvable both are the differentiate. There is a possibility that the non-convergent solution means method is not accurate and it is not giving the converse solution, but there is a possibility that the solution exists. But in this case you can say it is out of this, it is not cutting here for any demand, this is a unsolvable point. So what in this case, we normally fix the voltage, means we never estimate the load there. In this case, fix the voltage and then we correct this, and then we can reach this E point. So in this corrector step, normally the step is chosen in such a way that we should not go somewhere beyond, and then we can get the solution. So this method is no doubt is very slow and it is very time consuming compared to the conventional power flow method. So the slow, as you know here, every time we are moving with a small distance, tangent 1, and then we are using the predictor by solving the one load flow, then we are correcting one load flow. So keep on doing this till we are moving to the nose point. But this method will give the converse solution, no doubt in any case it will give the converse solution. So the selection of continuation parameter is very, very important. So initially lambda can be taken as the continuation parameter, but near to the critical point here at this point, what should be your continuation parameter? That parameter, this xk, or you can say tk, is the maximum of all these tangents. What is the difference? This t, what is the t1, t2, all tn? There are nothing but your change in your delta, change in your v, and change in your lambda. So here which will have the highest value, that is taken as the continuation parameter near to the critical point, or you can say nose point. Sensing the critical point, this can be observed by looking at the change in the lambda values. Before the critical point, normally here this change in this will be positive, at the critical point it will be 0, and the post critical it is negative. Means here during this zone here change in the lambda, change in d lambda is always positive. Here at this point it is 0 and lower point here it will be your change in lambda, it will be negative. Now we can get other information as well from this continuation load flow method, and that is basically we can get the sensitivity information. That sensitivity information that we can get from the tangent vector, because tangent vector is change in the angle, voltage and your loading. So continuation method can be used to identify the weakest bus in the system without any extra calculation. There is no need to go for extra calculation, and based on this continuation method we can get the weak bus system in this, so that we can know which one is the weakest bus and very close to the voltage instability point. Means weakest bus is the one which is closest to the voltage instability point, since load change at all the buses may affect the voltage at a bus. An index can be used to identify the weak bus in the system. You know this here whole big system. Let's suppose the voltage here at this bus, and you are keep on increasing there the various buses in the system. If you are changing here even the load, here the voltage at this bus will affected. It may be less affected, but it will be no doubt. So here it can be defined as the near to the collapse point or nose point. Collapse point is nothing but the saddle node point. Here again I have to say it, means here the collapse point is, this is your collapse point, that is nose point, sometimes called saddle node points, and here also called the singular. Here the Jacobian becomes non-singular. So the near to the collapse point, the change in the voltage at any bus here with the change in the P total, how much change, that is a P total means changing from one point to another point, that is tends to infinity, means it is very very high value, means if you are changing here your load, the change in the voltage will be very very high. How you can see here? Again from this you can see at this bus, means let us draw only the nose point here very clear. This is your P, this is your V. You can see here if you are changing the value this P and this P, the voltage change is very small, but you can see here and here this voltage was here and now the voltage is here. So at the nose point this value is tending to infinite. So what we normally do, we can get the maximum out of all these at which bus it is the voltage change is the maximum, and that will be the weakest bus in the system. So if you want to go for the several weak buses, then you can rank them and then you can pick up which are having the highest value of that is change in the voltage of that bus with the change in the total power, and here we are talking about the real power. The reverse of this, if you can go, this will be change in the total real power with the change in voltage, it is tending to 0. The reverse is also true. So what we can do, it is the change in the total here, it is nothing but some factor C and change in the lambda. The change in lambda here, this is also C is some constant because some initial loading, and then we are changing the lambda. So this is also we can say change in voltage with the change in here we can say lambda, that will have the maximum value. We can also use for the reactive power, means here instead of P total we can use some Q total as well, and then we can also identify the weakest bus using here your the total reactive power change, and then again we can have the different buses for the different one. So this sensitivity information is very used to identify the weakest bus in the system, and that weakest bus system is very close to the voltage instability point. Now the proximity indicators to the various proximity indicators to static voltage instability. Again the voltage instability can be classified into the two types, one is the static, another may be your dynamic voltage instability. We will come to the later about the dynamic stability, dynamic voltage instability condition. To see what are the various proximity indicators for this static voltage instability. First one is the load margin based on your PV or QV curves, and it is true only for the radial power system. Means here this is your as I said, this P and this V, especially it is valid this one, how much margin you are having from here. Let us suppose you are loaded at this point. So, this distance is called the load margin, means point here is the nose point, this is your actual operating point, and this is your called the load margin. So, we can say if you are having more load margin in the radial system, we can say your system is more stable. If you are operating very close to nose point, then you are very close to the voltage instability condition, and that is true only for the radial systems only. Similarly, we can also go for the cubic curves, and again we can see and we can analyze that how close we are with respect to the voltage instability. Another indicator is, already I have discussed that is the minimum singular value or condition number of the load flow Jacobian. Means at this here we can go for the load flow Jacobian, here we can calculate, and then based on that we can calculate the sigmas. If you remember here, sigma, that is a condition numbers, or you can say minimum singular value, and means we can calculate the Jacobian the eigenvalue, which will be having the minimum value critical, and based on that we can calculate, corresponding to that we can calculate the minimum singular value. Already I have discussed that. So, this is one criteria that we can determine. Another, using the eigenvalue of the Jacobian, and especially we can use either full Jacobian, means using both real and the reactive power flow equations, means that is a full. We can use your J1 and J2 as well, means here J1, J2, J3, J4. Here this corresponding to your change in P, here change in Q, and that will be equal to your change in delta, here change in V by V. So, this is called full Jacobian, but we can also use the reduced Jacobian, and that is called the QV Jacobian. Here we can use the J4. Means what we do, we assume that if there is no change in the P, we can go for the QV relation, and then that will get the reduced Jacobian corresponding to J4, and this is normally J4 minus here J2, J1 inverse, here J3, and you can get it. Another is the closeness of multiple load flow solution in terms of voltage instability proximity indicators. So, VIPI, normally as power flow equations are nonlinear, and we can have the various solutions. So, multiple solutions are there. Again, if we are keep on moving to the critical point, the solution becomes one, and after that we cannot have the solution at all. So, the solutions for this radial system, you can see for a given P we are having two voltages. So, it has two solutions, and then you can see if you keep on load is increased, here only one solution, means both solutions are converging and both solutions will have the same value. So, in the power flow we can get the multiple solutions, and then we can find the closeness to the multiple solutions, and then we can go for the different index we can form, and that is called the voltage instability proximity indicators we can use. Another is energy function based measures, means we can use the energy functions, and we can see how much energy, means from boundary how much energy means you are having, and we can formulate the problem in terms of energy functions. The critical loading parameters from the continuation power flow methods here, means here the critical loading parameters, as you know, if you are operating, let us suppose at this point A, with the help of continuation parameters you can find that how much you can load your system to reach this nose point, that is a critical lambda critical, I can say, means you can only load your system up to that lambda critical. So, knowing this criticality, we can say how much you are close to the voltage instability, and this can be obtained using your continuation power flow method, which just I described. Other that we can use the change in the here the reactive power generation to the change in load, or change in E divided by change in V, that is your sensitivity measures, and this gives your voltage control proximity indicators. Means here if you are changing the voltage at one bus, how much voltage change in other system, or that is the excitation voltage. So, that can also give you some indicators for the voltage instability, and again it is static in nature. We can use the L index. Several people have suggested that L index is also very useful and the powerful methods to calculate this, to know that how far you are from the voltage instability point, and this index can be also used. Another is your closest distance to the saddle node bifurcation or the maximum loadability in load parameter space. As I said, here we can say how much distance that we have, closest distance, and that point is called your saddle node bifurcation point. So these are the various methods, those are suggested in the literatures, and here most of the solutions here, someone is very fast, someone is very slow, some gives only some relative information, some gives some more information. So we can analyze the static voltage instability using these various methods. Now let us always we try to calculate here the last point which I said here, the closest distance to the saddle node bifurcation point. Here in the 2-bus system it is very easy to calculate that this distance you can measure here, but what happens in this multi-bus system, or there are several bus system, then it is very difficult to calculate this. So what normally we do, we go for some method to calculate. For example, this is your PQ space, means this is your the space at all the buses, means here Pi and Qi, and that you can say it is a 2n space in this axis is there. So you are somewhere at point x here, and that is called your S naught, means your complex power is a P plus jQ naught. Here you are having this. Now I want to know this boundary is your saddle node boundary. So it is your hyper surface. It is not a simple surface. It is a hyper surface of the n dimension hyper surface, and we want to see how much you are close that. So we want to calculate this distance from this boundary. So this minimum distance, and that minimum distance is always, once it is here, it is that you can say it is a perpendicular to that point. So if it is forming 90 degree, this is not your minimum loading, this is not your minimum loading, because this angle is more, this angle is more. So we have to determine this S star, and that distance S star minus S naught, here the magnitude, that will give you the closest distance to the saddle node bifurcation point or maximum loadability in the load parameter space. Load parameters again, that is a P plus jQ. So consider a radial system having line with the reactance X and load P plus jQ. Now how we can determine that the difference between your S naught to S star? One method, that is a method number 1, that is you can use the iterative solution method, and that starts from the initial point S naught and moves in an assumed load direction. You can assume any load and increase in the direction, any assumed direction, till one of the Jacobian eigenvalue of Jacobian eigenvalues becomes 0. Say it is at point S1, you can see here, means here you are moving, you are increasing the load. Now here simply just we have increased the real power, keeping your reactive power constant, but you can go in any direction. So what happens, you are keep on increasing, and you have reached at this point, because that this is a surface where it is a saddle node bifurcation, means one of your Jacobian eigenvalue will become 0, means this Jacobian becomes singular at this surface. This surface is, you can say, it is called singular node bifurcation point. So you are moving here at the point S1 you have reached, your Jacobian becomes singular. So corresponding to that eigenvalue which is 0, you can calculate your left eigenvector, that is a psi 1, corresponding to the critical eigenvalue, that is 0 in your case. This you have to note it at the saddle node bifurcation point. This is tangent to this surface. This is your surface, means this is your surface, and this value will be the tangent to this. So what you can do, just you have calculated here and then you got the direction tangent. So now after getting this direction here, now you can again come here and now you can move your load in that direction here. So in that case you may come to another point, let us suppose here in that direction here, and you have achieved your S2. Again this S2 is not your optimal point, means this is not the distance here because the minimum distance is here, we want to calculate this minimum distance. So this point also S2 you have to calculate. Here as you know this boundary your Jacobian determinant become 0, means you will have one eigenvalue 0. If we are having that one eigenvalues, then corresponding you can calculate the left eigenvector again, and let us suppose you got the psi I2. This will also give you a direction here and that will be a tangent. So again with this direction calculation again you come here and then you can move to another point here, and finally you can again moving the tangent and you have arrived S star. At the S star now this will be here, this point here, there will be no further change, means here no change in the critical loading values, and this S star minus S naught gives the closest distance to the saddle node bifurcation surface in the load parameter space. So let us see next method, that is method number 2, and which uses the optimization method. In this what we do, we formulate the whole problem into one objective function, and that objective function is nothing but it is the Euclidean distance, that is f, and which minimizes the distance between the minimum distance it finds out, and that here you can say this distance we have to find out. So what we starting from here we have to move at this boundary. This boundary is again saddle node bifurcation point, and then when it gets a minimum value then it will stop and again subjected to the various constraints. So here your objective function is a scalar objective function f, which is the difference between your s, that is we are going to find out what will be the value of s, minus s naught where this your initial operating point was there. So here it is a transpose one. So here s is the vector, means vector on all the buses, that is a si means s1, s2, s3 and so on so forth. So here just we are difference, then we are multiplying with the transpose, means we are getting here a scalar value. The half is used is since one constant, optimization will not change at all if you are multiplying by any constant, only we have since here that if you are differentiating it here this 2 will be vanishes. So this is your objective function, means we have to minimize this function f, that is minimum of f, subject to various constants. Constants here are nothing but your power balance equations, that is here, that is your I can say f, that is a delta, and here v is equal to 0. In this case what we are going to achieve here, this value f delta here, this is corresponding to both the real and reactive equations. So you have the equality constants, then you have your inequality constants, means that is a limit on your various things, limits on your power generation, limits on your the voltage, limits on the tap. So we can have the equality constants here and we have the inequality constants, and this is your conventional optimization problem, and that can be solved by any nonlinear programming techniques. Here this problem is highly nonlinear. So the selection of this method, although you must be knowing there are so many optimization methods are there even though in nonlinear, but they are some are having inherent problem, and then you have to choose very, and also there is a initial guess is very very important. So initial guess we start here from S naught, and then we can find some initial guess and then we can get the optimal solution. So at that point that S and B condition, here the Jacobian, the determinant here becomes 0. So we can optimize and we can get it, and then here the solution here you will get it here S star point, and then you can calculate the distance, that is your d distance will be your S star minus S naught, and here then you can say how much loadability that you have in your system, and that gives your information about the voltage instability point. Now come to the dynamic voltage stability analysis. and normally for that we use the bifurcation theory. The bifurcation is nothing but a qualitative change in the behavior of any dynamical system. Whenever there is a qualitative change in the behavior of the dynamical system, then that point is known as the bifurcation point. There are the two types of, we can classify the bifurcation into the two categories. One is your local bifurcation and another is your global bifurcation. Local bifurcation basically emerges out of fixed points. Fixed points are nothing but your initial equilibrium points. Bifurcation by observing the behavior of model in a small neighborhood of an equilibrium. Means equilibrium point here, if your equilibrium point is this, then we normally go for the small neighborhood of this one, we go for and we analyze this. Example of this local bifurcation is nothing but your saddle node bifurcation, that is S and B, the pitchfork bifurcation, transcritical bifurcation, and another is your half bifurcation. This local bifurcation is nothing but it is your static bifurcation, it is also known, except your half bifurcation. Global bifurcation is nothing but it is your dynamic bifurcation that emerges out of a periodic orbit. The qualitative change in the phase portrait not restricted to the small neighborhood of an equilibrium point. This has several examples, and that examples are periodic doubling bifurcation, PDB, cyclic fold bifurcation, and the torus bifurcations, and chaos, of course, chaos is one of them. So, all the global bifurcations and half bifurcations are also called the dynamic bifurcations. Means here in local, if you exclude this half bifurcation, then it becomes static, and if you include the half here in the global, it becomes your the dynamic bifurcation. So, we can categorize in the dynamic bifurcation and in static bifurcations. Now, let us see the various bifurcations here. First, we can see this saddle node bifurcation, that is a very as already in static we discussed the saddle node point, saddle node bifurcation point, that was nothing but here you can see it is a node point here, and we were calculating. So, the in saddle node bifurcation, you can say in all the cases Jacobian with respect to the states is singular. Here you can see here your Jacobian becomes singular, here it becomes singular, here it becomes singular. So, this is the point where your Jacobian becomes singular. So, in all the cases Jacobian becomes singular. The condition for the Jacobian with respect to the parameter, means parameter, that is load or whatever you can say here mu parameter, and the Hessian differ in the each type of above bifurcation. So, this parameter value is keep on changing, but all are having the Jacobian point here. These are the bifurcation points at this point. So, in the saddle node bifurcation point that we can categorize here, you can see here this is the stable part, and it is here you can say suddenly lower portion is unstable. So, this is your stable, this is your stable, and here this is your unstable. So, it is a qualitative change. At one point you can say the system becomes stable and then suddenly it becomes unstable, then this point is called the saddle node bifurcation. Means it is a point between the two stable and unstable points in general way you can say. So, this is your saddle node bifurcation. To have the condition for the saddle node bifurcation, it is the defined as that if you are having, means we can any dynamical system I can say it is x dot is equal to your any function f, that I can say here x into some p. P is your disturbance vector, that is a changing, something changed. For example, let us suppose it is a load r mu that I have considered, and x is the state vector and it is describing your state. Now, if it is your dynamic system, that is a x dot, that is it is nothing but dx upon dt, that is changing with the time. Now, for the condition of this here, the for saddle node bifurcation, the first condition here this f 0 0 here is equal to 0. Means here if you are putting x is equal to 0 and the p is equal to 0, it is 0. You can see here at the mu 0, everything here 0. Means here mu value is starting from 0 here, you can say x is also 0 and mu 0 at this point. This is the first criteria. Another here your del f with the change x here, and again add the 0 0, it will be 0. Here your double differentiation of x here, and that will be not equal to 0, and also del f here, del mu in this case p here, it should be not 0. To have the example for this, so these are the condition for your saddle node bifurcation. To have an example, let us see an example here, that is your x dot is equal to mu minus x square. Now this is your dynamical system, and then you can see here x dot is equal to 0. Here we are getting the solution, means your equilibrium point here, that is the mu minus x square barabar 0, means I can say x is equal to plus minus mu. So this is your solution point. Now when x is 0 and mu is 0, we are getting this value. Now if you are differentiating this function, this is your f(x). So if you are differentiating with the x, you are getting minus 2x is equal to your del f upon del x. So and putting 0, then again you are getting 0. So you are satisfying this one. Now if you are double differentiating this, means your del f del x square is minus 2 and it is not 0. So you are meeting this one as well. If you are differentiating with respect to here mu, and you are getting your del f upon del mu, you are getting unity, which is not 0, means it is not 0 because it is equal to 1. So we are meeting this one, and then it is called the saddle node bifurcation. Here if you can see here the point which is coming here, and here it is suddenly it is unstable, and it is called your saddle node. And this is nothing but a equation of parabola, that is a mu is equal to x square here, that is a starting point. Now let us come to your other bifurcation point. Let us see the transcritical. In the transcritical, the condition for this one here is similar, means we can have your condition, that is f 0 0 is equal to 0. Here your change in your f with your x 0 0 is 0. Here your del square f over del double differentiation is not equal to 0, and here we want to have del f over del u del x double differentiation here should not be 0. So these are the 4 conditions for your transcritical, and the example for this, if I can put here x dot is equal to your mu x minus x square. You can see if you are putting mu is equal to 0 and x is equal to 0 here, and this is nothing but your f x and mu here. If you are putting this x 0 mu 0, you are getting this. If you are differentiating this with respect to x, so you are getting and putting 0, you are going to get this. Here if you are double differentiating this, you are getting minus 2, which is not 0, and if you are differentiating with respect to your mu, then you are differentiating with respect to x, you will not get 0, and then you are satisfying this. So this is your transcritical bifurcation. Here you can say the point of the bifurcation, again here the point that we are starting, that is here f x u is equal to 0. Means if you are solving this, what is showing? This is showing your x mu minus x is equal to 0, means it shows s is equal to 0, and here your x is equal to mu. Means you are having the two. If you are drawing here mu and x, you can see this is your x, this is your mu. So one will be here starting point, that is one equation, and your mu is equal to x is a linear equation, and this is your linear equation. So at this point here you can say this is your stable point, the stable curve, this is your stable curve, but these two dotted lines are unstable. So at the point where stable and unstable your characteristics are meeting, it is called transcritical. Here you can see it is a transcritical. So the condition for the transcritical bifurcations are this, and the example for this as I explained here. Another one is your pitchfork bifurcation. This is slightly different than your saddle node bifurcation, but you can say this here, this diagram is almost similar here. Only difference here, this is a quadratic, here it is not there. It is only this curve which is coming here and this point it is stable and unstable, but in the pitchfork it looks like a fork, and you can say this is a handle and this is your fork, and then it is called pitchfork. The condition for the pitchfork bifurcation here, we go for all these 3 points here and we add several more. So, these 3 are true here, and then we are adding here. So, that is a mu f or mu u or mu x here, that is not equal to 0, means you can say transcritical plus 1 extra, and that extra here is your triple differentiation here with respect to x3. Here it should be not 0, at here at point 0 0 here it should not be 0. So, here we can see at this point an extra point is added, and then here at this point we can say this is your stable, this is your stable, this is stable, and here is one is not stable. So, this is the 4 curves, means 1, 2, 3 and 4 are combining here. Out of that, 1 is unstable and 3 are stable. In this case 2 are stable, 2 are unstable. Here 1 is stable, another is unstable. So, 1, 2 and 3, and you can say now it is a pitchfork bifurcation. The example for this, here we can have example, that is the x dot is equal to mu x minus, here if you put x3, then this is example of a pitchfork bifurcation. So, these bifurcations are used where for the dynamic analysis, and that is very, very important. So, another dynamic bifurcation, here this is a, all 3 are the dynamic bifurcations. Another is one your, that is called half bifurcation, and that comes under the local bifurcation category. So, the dynamic bifurcation, that another is half bifurcation, and that is very, very useful for the getting your dynamic stability in the terms of voltage. Here I am talking. So, half bifurcation takes place whenever the Jacobian has the 2 pure imaginary eigenvalues and the remaining having the non-zero real part. Again you can see here in the saddle node point bifurcation, here I said the Jacobian here complete, here it will have the determinant is equal to 0, means one of the eigenvalue, means it is a rank dipset. So, one of the eigenvalue will be 0, but in the half bifurcation here the determinant is not 0, but the eigenvalues here, the pair of pure eigenvalue, means normally I can say the lambda I, it is nothing but your alpha I plus j, I can say beta I. So, here this will be 0. So, we can say we will have the pure, and again it will be the conjugate. Always if you are having the imaginary eigenvalues, it will be in the complex conjugate pair, means one will be the plus, another will be minus. So, here this real part of this eigenvalue is 0. So, this is not the determinant is 0, but here the real part of the 2 eigenvalues are 0, and then here we can achieve, and that is known as half bifurcation point. It is characterized by emergence of periodic orbit around an equilibrium point, means it is a periodic point around one equilibrium point. This is the point, that is nothing but your, here I said x dot is equal to 0, this will give you the equilibrium point. So, if the lambda, that is a here, that is a parameter of loading parameter P or disturbance parameter, then this is eigenvalue. Here this is lambda is eigenvalue, wherever in the continuation power flow lambda I was using the loading factor. So, this lambda is the different than the continuation power. Here is the eigenvalue. So, eigenvalue corresponding to any loading parameter P, that I can say alpha plus minus j beta is a pair of complex conjugate. The eigenvalues at the SP point, here it will be having 0, and for others it will be remaining, it should not be 0. So, if here alpha remaining sum of the alpha, if it is 0, then we can say this half bifurcation is degenerate. Also, this half bifurcation is classified into the two different categories. One is called subcritical and another is called supercritical. Means in subcritical, if unstable equilibrium orbit surrounds the stable equilibrium points, means here there is a possibility that this x naught, whether the solution here is stable or not. So, we can have the equilibrium point here putting x equal to 0, whether that is a stable or not. So, if it is a stable and it is surrounded by unstable periodic orbits, means here this is your unstable points, here unstable points, and it is going out, and this is your stable equilibrium point, then it is called subcritical. Means here is stable, outside it is surrounded by unstable orbits. However, in the supercritical, here your equilibrium point here is unstable, one stable equilibrium point, and then it is surrounded by here you can say stable orbits, and that it is called supercritical. When a parameter says the loading is varied, half bifurcation may take place even before saddle node and thus limiting the margin of stability. So far in the static, what we were considering, this is your this point, and we were going up to this saddle node bifurcation point, and then we are saying if your loading is here, then this distance is your the margin that you are having to the collapse point. But this saddle node point may be even though earlier to that saddle node point, and then you cannot load beyond that because your system becomes unstable, and that is called half bifurcation point, and then we have to measure the distance from here to this one, and due to the dynamics of the nature of the system. So, you can see in any system here your eigenvalues may have a real only, may be having the complex conjugate, and may be having this positive. Means here you can say your lambda can be alpha, here lambda can be here alpha plus minus j beta. There is a possibility if beta is 0, means you are having, and this value can have the negative, 0 or positive. If this alpha is positive, this zone, then it is called unstable at all. If it is negative, then it is in here your left half plane, and then it is stable, and if beta is 0, then it will lie on the real axis. There is a possibility that here alpha and betas are not 0, then we will have the pair of roots here, a pair of eigenvalues, and if you are keep on increasing your load, then what will happen, they may move and they may vary, and here they may cross at this imaginary point. So, at this point when they are crossing the imaginary point, that is called your half bifurcation point. So, the two complex conjugate eigenvalues cross imaginary axis as parameters are changed, and here we are talking about the load parameters. So, this is your, at this point you can see this becomes 0, and only we are having the pair of this eigenvalue, that is imaginary values. Now, the subcritical here and the supercritical, you can say this is your solid line is your stable line, and this point is called unstable periodic orbits, and it is surrounded by your stable. So, it is subcritical. Here your this is a stable periodic orbit, and here is your stable zone, here it is unstable. So, it is surrounded by your unstable. So, this is your half bifurcation. So, we have seen that the bifurcation for the static we have different criteria, and then we can go for the analysis of this using the different proximity indicators, and then we can analyze the static voltage instability. Whereas, if you are going for the dynamic voltage instability, you have to use the bifurcation techniques, and this half bifurcation is one of the very important which normally occurs before the saddle node bifurcation point. So, you have to go to determine the half bifurcation point, and then you can say how much you have your dynamic voltage stability point margin, and then you can decide your parameter or system operation, and also in sometimes case of the designs one. So, in the next we will see the various other bifurcation techniques, and then we will give some examples for how this other devices like FACTS that can improve your dynamic stability as well. Thank you.